Hello, welcome to this video produced as part of the Further Maths Support Programme's material for A-Level Maths and Further Maths. This one is the second in a series on dimensional analysis and focuses on the concept of dimensional consistency. Let's do a reprise of the three basic dimensions: mass measured usually in kilograms, length measured in meters, and time measured in seconds. If we want to add, subtract or equate physical quantities, they must have the same dimensions in order for the operation to be meaningful. Using this idea, we can test whether a formula is dimensionally consistent. So, could this formula presented here be correct? Look briefly at the foot to confirm that the letters mean what you think they mean. V corresponds to volume, R to radius, and H to height. Now the formula seems to be saying that a volume is equal to what we may recognize as the volume of a cone. But that's added then to a term which represents usually the circumference of a circle. It's not possible to conceive of any situation in which you would be adding the volume of a cone to the circumference of a circle. That just doesn't make any kind of sense. And that, in a nutshell, is the idea of testing for dimensional consistency. So let's see how that works out with a formal analysis. It won't tell us anything new, but it shows how we can argue in a more formal way. The V term would have dimensions of L cubed, because it's a volume. 1/3 pi r squared h, if it isn't obvious, would be analysed by saying that a third and pi are dimensionless numbers, and then r squared is L squared and h is L, so we get L cubed again. And 2 pi r, again 2 and pi are dimensionless numbers, times a length, so the dimension is L. Now that seems to be saying that an L cubed term is equal to the sum of an L cubed and an L term, and that is inconsistent, and therefore we dismiss that formula as nonsense. Let's look at that in a little bit more depth. Here we got three equations proposed for consideration. Check what the letters mean. F corresponds to force, d to distance, m to mass, t to time, and u and v to velocity. Let's look at what the dimensions of each of those terms are. So, in the first case, the first term that comes up is Fd. That's a force times a distance. Well, force we can quote from a previous video as mlt to the minus 2, and that's times an L term, so finally that's ml squared t to the minus 2. The second term that appears is mv. That's equal to mass times velocity, so that's mlt to the minus 1. mu would be the same. We should strictly write it down, but I'll save space by remembering that it's the same as mv. ft comes next, and that's force times time, so that's mlt to the minus 2 times t, so that gives us finally mlt to the minus 1. mv we've already done, and we've already assumed mu is the same. fd we've also done, and finally we've got a half mv squared. So half is dimensionless, and that's mass times velocity lt to the minus 1 squared, so that gives us ml squared t to the minus 2. Okay, now armed with that information, let's check the equations one by one. If we take the first equation, which I'll mark by 1 asterisk, check the fd term, it's mlt to the minus 2. The mv term, however, is mv to the minus 1. So you've got a dimensional inconsistency there. We don't need to go any further. That one can't be correct. Now look at the second one, which I'm marking by 2 asterisks. Here you've got an ft term, which has dimensions from the right mlt to the minus 1. And that does match the mv term. That also is mlt to the minus 1, and mu will be the same as we've already agreed. So that one is acceptable from dimensional consistency's point of view. The third one, fd, we've already met. It's ml squared t to the minus 2, and that matches the same ml squared t to the minus 2 of a half mv squared. So the third equation, which I'm marking just for consistency with 3 asterisks. That one is consistent, so that one would on the face of it be acceptable. Now the second equation you'll recognize very possibly as the impulse momentum equation. So we verified that is dimensionally correct and dimensionally consistent, I should say, strictly, and equally the third equation is the work done equals change in kinetic energy equation, so not hardly surprising that one's correct as well. The first one looks distinctly dubious, as it seems to be equating work which is not associated with momentum. So there we are, that's the end of this video presentation. The next one in the same series will push the idea of dimensional analysis into a more constructive mode when we consider ways of trying to formulate unknown equations using dimensional consistency. I hope to be with you later to explore that.